Next we start the next section on determinants. Let us start with this system of equations where the unknown quantities are x1 and x2 and all these coefficients alpha ij's and these quantities betas are coming from some field f. That field is not necessarily the field of real numbers or the field of complex numbers, it's any field. And here is a question about this system. Under what condition on these coefficients alpha ij's is the above system solvable? We can rephrase this question like this also. In place of this system of two equations in two unknowns, we can also write this matrix equation, where you can see these coefficients forming a matrix, which often is also called the coefficient matrix of such a system of linear equations, and followed by this column of the unknown quantities, which is also a matrix. And on this side also we have the column matrix of these betas. Under what condition again on these alpha ij's does the matrix A means this matrix is being called A, map F2 onto F2? Recall that F2 is the vector space of all ordered pairs of elements of the field F. You may think of these columns as those ordered pairs. Actually, they are not, strictly speaking. For example, this matrix is not an ordered pair, but this matrix can be thought of in place of the ordered pair whose first coordinate is beta 1 and second coordinate is beta 2. And in what sense is this matrix mapping F2 into F2? In this sense, that you multiply any element of F2 by this matrix and you get another element of F2 in that sense. But why are we asking this question here? You see, this is an unknown vector in F2, right? If we think of it as a matrix, in place of the ordered pair x1, x2, you are thinking of it as this column matrix. This is an unknown vector on which we are applying the matrix, and we are getting this known vector. And we are asking under what condition on the entries of the matrix is this going to be possible for any vector on this side, so that if this is given, regardless of what this is, you are always going to get a pre-image under this map, the map which multiplies the matrix and this column matrix. Under what conditions on the alpha ij's will this map F2 onto F2, so that for anything here you get something here, so that this equation is true, or in other words, so that this system has a solution. Now, if you go the usual way of eliminating one of the unknowns, say x1, or you can try to eliminate x2, and then from those two equations where there is no longer x1, only x2, you then go for solving for x2, and then you quickly realize that you need this condition for to be able to calculate x2 from whatever ultimately you get after doing elimination and manipulating the things. You want alpha 1 1 alpha 2 2 minus alpha 2 1 alpha 1 2, or alpha 1 2 alpha 2 1 to be non-zero, because this appears as the coefficient of x2 on one side, and on the other side there is something else. So if it is 0, of course from that you cannot calculate x2. x2 can be anything then. The left hand side will be 0, the right hand side will also be 0, and the equation ultimately comes in this form: 0 times x2 is equal to 0. But there you can put anything in place of x2, any field element. So that's not a condition for solvability. For solvability, this is what you need. You need the coefficient of x2 to be non-zero, which is what this is. So this is the condition. And now next we are also going to consider another such system of equations, again a system of linear equations, but this time with 3 unknowns, and we are going to see 3 equations also. And that system is this, consisting of these 3 equations, and you can see that here there are 3 unknowns, x1, x2 and x3. And the coefficients, actually you know in what pattern we are writing these suffixes I and j. The first suffix of your alphas denotes the equation in which that is the coefficient. And here in the first equation all the first suffixes are 1 because it's in the first equation. 1, 1, 1. And the second suffix denotes the variable of which this is the coefficient. 1, 1 because it's the coefficient of x1. Variable means unknown. 1, 2 because this is the coefficient of x2. Like that the other alphas have also been indexed. And on this side again you have some betas. And all these alpha ij's and all the beta i's are again some elements from our underlying field F. Here also we ask that question, under what condition on these alpha ij's is this equation, is this system of equation solvable? And the condition for solvability in this case is quite complicated. It is this. This expression should be non-zero. Let's see for a moment what this expression is, what it has. You have alpha 1, 1, alpha 2, 2, alpha 3, 3 plus alpha 1, 2, 2, 3, 3, 1 plus 1, 3, 2, 1, 3, 2. But then after that you have minuses. We cannot quite figure out so easily how these signs are being determined. That is, these 3 terms are coming with a plus sign, but the other 3 terms are coming with minus sign. And this one, here the coefficients come in this pattern, alpha 1, 2, 2, 1, 3, 3, 1, 1, 2, 3, 3, 2, 1, 3, 2, 2, 3, 1. What is going on? Here also you see things start with having the same suffix 1, 1, 2, 2, and then immediately here minus comes and 1, 2, 2, 1 comes. So we first of all have to make a guess. Of course we can guess just about anything from these 2 situations, but this is what we notice about these expressions. Let us first decipher the easier one between these 2. You recall the symmetric group of degree 2 from group theory. It is the group of all permutations on a 2-element set. And you know that S2, which is of course S2, the group is S2, has 2 elements itself also, 2 factorial. One of them is the identity permutation, and for the sake of simplicity, obviously we can consider, let me write it here, we can consider this to be the set on which we are thinking of the permutations set. So your identity permutation maps, permutation is after all a function, right? A one-to-one onto function from S2 itself, and this function which we are calling iota maps 1 to itself and 2 to itself, so it does not change anything. What does this other permutation do? We are calling it sigma, and here we have used the cycle notation. You already know these things. Sigma maps 1 to 2 and 2 to 1. Okay, so it maps the elements of S onto again the elements of S in that way. And these are the only 2 permutations that we have on S. Now we are going to rewrite this expression, we won't write not equal to 0, that of course is there, in terms of these permutations, like this. What do you see here? 1, 1. Now in place of this second one you can write iota of 1. because iota of 1 is equal to 1. 2, 2. In place of this second 2, you can write iota of 2 because iota of 2 is equal to 2. What do we do here? In place of this 2, we can write sigma of 1. Sigma of 1 is equal to 2. Sigma interchanges the two elements. And in place of this 1 here, after 2, you write sigma of 2 because sigma of 2 is equal to 1. So in this way, we seem to have figured out how the coefficients are coming. Note one more thing, that in both these terms, this is the first term and this is the second term, all the elements of S are appearing first as the first suffix 1, 2, 1, 2, and then followed by the image of that element under the permutation that you are choosing for that. For this term we are choosing iota, for this term we are choosing sigma. Okay, but what about these signs? Here we have plus, here we have minus. Where is that coming from? To see how that is also determined by the choice of our permutation, you recall the definition of an even permutation and an odd permutation. When do we say that a permutation is an even permutation? It is when you express a permutation as a product of transpositions, that is 2 cycles, which you can always do. You already know this fact. That there are an even number of 2 cycles involved, then it is called an even permutation. But if the number of cycles in such a product, which you can think of as a factorization of the permutation also, if that number is odd, then the permutation is odd. Now it turns out that you can express a given permutation as a product of 2 cycles in multiple ways. However, the number of 2 cycles appearing in any such factorization, its parity does not change. That is, if it is even, if you have found a permutation as a product of 2 cycles, then you may be able to express it as a product of 4 2 cycles also, but never 3, never 5. If it is even, then it will continue to be even. That evenness will not be lost. And the same is also true for odd permutations. Alright. How can you express this identity permutation? We can express it as 1, 2 times 1, 2. So in that expression, 2 cycles are involved. So this is an even permutation, and whenever an even permutation is involved, you have plus sign. Whereas this permutation is itself a 2 cycle, and the number of 2 cycles in this representation of the permutation as a product of 2 cycles is 1, and 1 is odd. So that's why you get a minus sign. This is a very peculiar and arbitrary way of thinking of this expression in terms of permutation. But is it going to work here also? Let's see. So we need more space for this, so I used that part and this part as well. Here we need to consider this set of force, because we have 1, 2 and 3, and we are considering the group of permutations on this set, that is the symmetric group of degree 3, whose elements you already know. This is your familiar S3, your first example of a non-abelian finite group. Non-abelian group, in fact. So you have this identity permutation, these 2 cycles, 1, 2, 2, 3, 1, 3, and these 3 cycles, 1, 2, 3, 1, 3, 2. How many elements should this group have? It should have 3 factorial elements, that is 6 elements, and we have 6 elements. Plus you know, actually you know a lot about this group. You already know that this, I have named them, okay, so that we do not have to write this cumbersome cycle notation. This I am calling your iota again. So this is alpha, this is beta. Do not confuse this alpha with this alpha, okay. This is alpha, this is beta, this is gamma. Alpha is 1, 2, beta is 1, 3 and gamma is 2, 3. And these 3 cycles I am naming delta and epsilon. Delta is 1, 2, 3, epsilon is 1, 3, 2. And now we try to express this expression just like that using these permutations. The first term is alpha 1, 1, alpha 2, 2, alpha 3, 3. So 1, 2 and 3 of course will appear. This 1 is iota of 1, 2 is iota of 2 and 3 is iota of 3 because iota is the identity permutation. It does not change anything. And why do we have plus here? Because this is even. Oh, and we also know which one of these are even and which ones are odd. Let me put a plus sign over the even permutations. The 3 cycles are even. If the length of a cycle is odd, then it is an even permutation. If the length is even, then it is odd. And these 3 are odd permutations. Because this is even, so here we have a plus. Next we have 1, 2, 2, 3, 3, 1. So you can see that you can write in place of this 2 delta of 1. Because delta of 1 is 2, delta maps 1 to 2. The cycle maps 1 to 2, so 1 delta of 1. With 2 we have 3, delta maps 2 to 3. So in place of 3 we write delta of 2. And 3 to 1, in place of this 1 we can write delta of 3 because delta of 3 is 1. And this is also an even permutation, so there is a plus before it. What about this one? 1, 3, 1, 3. So this 3 can be written as epsilon of 1. Next, this 1 can be written as epsilon of 2 because epsilon maps 2 to 1. And finally, this 2 can be written as epsilon of 3. Where is it? Epsilon of 3. Am I saying it correctly or did I make any mistake? No, okay, because this one I have already considered. Okay, fine. So in place of this 2, we are writing epsilon of 3 because 2 is epsilon of 3. Epsilon maps 3 to 2. And this is also an even permutation. So that is why there is a plus before this expression, before this term. And next comes this one with a minus sign. 1, 2, 2, 1, 3, 3. Do you already see in what pattern these suffixes are appearing? 3, 3, 1, 2, 2, 1. 1, 2, 2, 1, 3, 3 means 3 is not there. So here we can use alpha. Alpha of 1, alpha of 2, alpha of 3. Alpha of 1 is 2, alpha of 2 is 1 and alpha of 3 is 3. And this is an odd permutation. So there is a minus sign. Similarly, you will see that this next one, 1, 1, 2, 3, 3, 2, 2, 3, 3, 2. And 1, 1 means 1 is not there. Not there means it gets mapped to itself by the permutation gamma. So you have the gamma images here of 1, 2 and 3 respectively coming like this. This is an odd permutation, so a minus, and finally this one corresponds to beta because 1, 3, 3, 1 and 2, 2 remains means 2 remains the same under this permutation. Where is it? This one. So that's how, very surprisingly, our first guess of expressing that expression in terms of the elements of the symmetric group S2 turns out to also work here in this case, this time with S3. And with only these two cases, we are now going to define determinant of an n by n matrix. Do not forget that behind these two expressions, this expression and the one that we do not see here, alpha 1 1, alpha 2 2 minus alpha 1 to alpha to 1 not equal to 0. That expression, not the inequality. Behind both these expressions, there is a matrix. The first one was that 2 by 2 matrix, and for this one also you can think of that coefficient matrix whose ith row jth column entry is alpha ij, and we are going to call these expressions associated with those matrices, they are determinants, but this we are going to do for a general n by n matrix. So this is the definition of the determinant of an n by n matrix. Let A be an n by n matrix over the field F, that means it belongs to the matrix algebra Fn, whose ith row jth column entry is alpha ij. Then the determinant of A, denoted by this notation det of A, if you want you can enclose A within round brackets, is defined to be the following element of the field F, this element. So it is like that sum. Okay, in both the cases we had sum. What are the terms of this sum? Again you have those alpha ij's, that is their product in that pattern, where the first coefficient, the first suffixes are just those numbers 1, 2, 3 up to n. This time we are dealing with an n by n matrix, so you have up to n, 1, 2, 3, 4 up to n, followed by the sigma images of these numbers, sigma of 1, sigma of 2 up to sigma of n. However, there is this extra quantity also multiplied with this product, which takes care of the sign. It is actually, you see, minus 1 to the power sigma, you should not take it literally. It's not the sigma power of minus 1, that does not mean anything. But it's just a symbol whose definition you can find here. If sigma is an even permutation, then minus 1 to the power sigma means 1. That's all. Whereas if sigma is an odd permutation, then it means minus 1. And the sum has as many terms as there are elements in the group Sn, the symmetric group of degree n. So that's what determinant is. There are many properties of determinants which are useful and which actually we have used already many times in solving systems of equations and elsewhere. But we are going to study properties of determinants, general properties of determinants, which will tell us something about matrices themselves. And one of those properties we are going to see next. Before we see this lemma 691, I forgot to write something which comes after this definition, but that you already know. You remember that in school you used a notation for determinants of matrices. If the matrix is written as a rectangular array of numbers, then you write the determinant as that array but enclosed within two vertical bars. So the author also mentions about that notation. That's all. Now let us next see this lemma. In this lemma, you again consider an n by n matrix A over the field F, and whose ith row jth column entry is the alpha ij. And this matrix is a triangular matrix. It may be upper triangular, it may be lower triangular. Then its determinant is very simple. It is just this: alpha 1 1 times alpha 2 2 and so on up to alpha n n. That means the determinant of a triangular matrix is just the product of the entries on its leading diagonal, main diagonal. So the proof, of course, is available in the book, so you go through the proof and let's see if we can understand. It's not really that difficult. It's some kind of induction argument. So you go through the proof and let me know if you have any doubts. And we are going to, in the next linear algebra video, see further properties of determinants. So see you in the next video with more properties of determinants. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.